Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of quantum technology, and today we are discussing the quantum device. So in this quantum device we are discussing the squid. The squid functioning is based upon the Josephson effect. So here we define the types of Josephson effect. So first is a DC Josephson effect, which is a direct current crossing the insulator in the absence of any external electromagnetic field owing to tunneling. Means we can define the DC Josephson effect, which is a direct current crossing the insulator in the absence of any external electromagnetic field. Now, this DC Josephson current is proportional to the sign of the Josephson phase, that is the phase difference across the insulator, which stays constant over the time and maybe varies from minus IC to IC. So, IC means current, there is a point from one point to the another point from minus to plus, it will constantly flow. So, it can act as a perfect voltage to frequency converter. So, another type of Josephson effect is the AC. So, with a fixed voltage, that is the VDC, across the junction, the phase will vary linearly with time and the current will be sinusoidal AC, that is the alternating current, with the amplitude IC and the frequency and the particular frequency, and that will be the Josephson junction. So, another type of effect is also there. There is a inverse AC, which microwave radiations of a single angular frequency omega can induce quantized DC voltage across the Josephson junction, in which case the Josephson phase takes the form, and that will be the inverse type. Now, the Josephson devices based upon the characteristics of the Josephson junction are valuable in high speed circuit. So, this can be designed to switch in the time of a few picoseconds, and these are having a lower power dissipation, which makes them useful in high density computer circuits where resistive heating limits the applicability of conventional switches. So, parallel Josephson junctions are used in squid devices for the detection of the minute magnetic field. So, we will see how sensitive are the squid device. So, in the squid device, parallel Josephson junction are used for measurement of the electric field. You can see on the screen, these are the Josephson junctions and these are parallelly joined for measurement of the magnetic field. So, this Josephson junction have two superconductors separated by a thin insulating layer, and that can experience tunneling of Cooper pair of the electrons through the junction. So, the Cooper pair on each side of the junction can be represented by a wave function, which is similar to the free particle wave function. So, in the DC Josephson effect, a current proportional to the phase difference of the wave functions that can flow in the junction in the absence of the voltage. Means whenever we are not applying any voltage, still the current is flowing in the circuit. So, in the AC Josephson effect, this JJ will oscillate with a characteristics frequency which is proportional to the voltage across the junction. So, since frequencies can be measured with great accuracy, a Josephson junction device has become the standard measure of voltage. You can see on the screen how we are using the Cooper pair and how there is a barrier and that barrier is crossed and that will work. So, this is the example of the Josephson junction. So, the wave function which describes a Cooper pair of electrons in the superconductor is an exponential like the free particle wave function. Basically, all the Cooper pair in the superconductor can be described by a single waveform in the absence of current because all the pairs have the same phase. So, they are said to be in a phase coherent. So, here we can see that Cooper pair, you can see here there are the number of Cooper pair, but they are in a phase, that is why they are defined by the single waveform. The upper diagram you can see easily. So, after that it passes from the barrier, then it will just decrease. So, this is the phase coherent. Now, if the two superconductors are separated by a thin insulating layer, then quantum mechanical tunneling can occur for a Cooper pair without breaking up the pairs. Means in the two superconductors, if they are separated with a thin insulating layer, the quantum mechanical tunneling can occur for the Cooper pair without breaking up the pairs. So, Clark inversion, this condition as a wave function for Cooper pair on each side of the junction penetrating into the insulating region and locking together in a phase. So, you can see here in the diagram also it is coming, then again it is in the phase. So under these conditions a current will flow through the junction in the absence of an applied field. So, that is a DC Josephson effect. So, what is the Josephson voltage standard? We can see when a DC voltage is applied to the Josephson junction, an oscillation of the frequency we can have F Josephson is equal to 2E del V divided by H cut, which occurs at the junction. So, this relationship of the voltage frequency involves only fundamental constant and frequency can be measured with extreme accuracy. So, this Josephson junction has become the standard voltage measurement. Now, the standard volt is defined here. The standard volt is now defined as a term of the Josephson junction oscillator. So, the oscillation frequency of a Josephson junction is given by F Josephson is equal to 2E del V divided by H cut. So, the relationship between the frequency and the voltage across the junction depends only upon the fundamental constant, that is E and H cut. So, for 1 microvolt, if we just have the value of the voltage, that is 1 microvolt applied to the junction, then the frequency we will get is the 483.6 megahertz. So, for the voltage 1 microvolt, we are having the frequency that is 483.6 megahertz. So, the standard volt is now defined as the voltage required to produce a frequency of 483,597.9 gigahertz. So, what material we use in the Josephson junction? Basically, Josephson junction consists of a barrier material sandwiched between the two superconducting electrodes, where the barrier acts as a weak link between the superconductors. So, what material we use depending on its nature? This weak link can be insulating layer, and a normal metal or a narrow construction given to the system, which give rise to the different classes of the Josephson junction, that is the SIS, SNS and the construction junction. So, over the year a wide variety of the material have been explored for both the electrodes and the barrier in order to optimize the junction performance for the specific applications. Now, if we are preparing, it depends upon the material and devices which we are preparing. On the basis of the materials are selected. So, material selection in the Josephson junction is governed by the several factors, which includes the dielectric loss, structural and chemical stability, aging behavior, superconducting transitions temperature, and ease of fabrication, interference, uniformity and the roughness, and the presence of two-level system. So, these are the basic features which keep in mind just to select the material for the preparation of the Josephson junction. So, what are the electrode material used for this JJ junction? The choice of the electrode material depends on the intended applications such as transmon, qubit, squid or detectors, as well as the fabrication capabilities. So, a key requirement for the superconducting electrodes is the sufficiently high superconducting transition temperature, which sets the superconducting energy gap and directly influence the current voltage characteristics of the Josephson junction. So, aluminum is the most widely used electrode material, that is the state of the art qubits due to its ease of fabrication and high quality of its native oxide barrier. So, aluminum are used. Niobium and tantalum that are also commonly employed and offering higher transition temperatures and improved robustness, while materials such as niobium nitride and niobium nitride provide even higher TC value for specialized high frequency or detector application. So, these are used for the various application. Depend upon the various application, the materials are used, right. So, the squid as a magnetometer, a superconducting quantum interference device, uses the properties of flux quantization and a DC Josephson effect to detect the very small magnetic field. Means the squid work on the flux quantization as well as the DC Josephson junction. So, they are sensitive enough to measure the fields down to the range of 10 to the power minus 15 Tesla. For comparison to a typical refrigerator, magnet produces a 0.01 Tesla, and the some processes it is used for the 10 to the power minus 6. So, central element of the squid is the ring of superconducting materials with one or more JJ's, Josephson junction. An example we will show in the figure, and the critical current that is defined by the IC of the junction is much less than that of the critical current. Critical current of the junction is much less than that of the critical current of the main ring. So, this produces a very low current density, making the momentum of the electron pair small. Now, we can see here that this is the circuit diagram of the squid that you are seeing here, that we are having the two part and how the J1 and JS, the Josephson junction J1 and J2, two Josephson junction we are using here, and this is superconducting which is separated by a insulating material. Now, we can understand this working of squid, that we consider the scenario when we bias it with a current well below its critical current value. When we bias it with the less value of its critical current value, then if we apply a tiny magnetic field to the squid, the applied magnetic field tends to charge the superconducting wave function that is defined by the R. So, but the superconducting wave function does not want to change. So, it must maintain an integral number of wave function cycle around the loop. So the superconducting loop does what we would expect. It opposes the applied magnetic field by generating a screening current, and is that is a IS. Means it is just oppose the applied magnetic field by generating a screening current that is defined by the IS that flows around the loop as we have seen. Now here this IS is moving around the loop that has been opposed by the that will because of created because of the opposition of the applied magnetic field. So the screening current creates a magnetic field equal but opposite to the applied field. This screening current will create a magnetic field which is equal to but the opposite to the applied field. So the effectively cancelling out the net flux in the ring. So in this way the applied magnetic field has lowered the effective critical current of the squid. So in other words, it has reduced the amount of biased current, or so we can pass through the squid without operating a resistive voltage. So since the screening current has superimposed itself on the top of the bias current. So the situation is depicted in the diagram as we have seen. So where IS flows parallel to the I biased by 2 in one of the arms, increasing the total current. So making it more likely to achieve the superconducting to normal transition. Now as we increase the applied magnetic flux, the screening current increases. But when the applied magnetic flux reaches half a flux quantum, something interesting happens. The superconducting junctions momentarily become resistive. So if we try to observe this transition in terms of screening current, we conclude that in order to lower the energy at phi is equal to phi 2 is not by 2, it will be the half. It is a little easier for the squid to keep 0.49 flux quanta in rather than keeping the 0.51 flux quanta out. Of course, the screening current will have to change the direction at this point. So variation of IS means screening current with is shown in the diagram. As you can see, this the phi is changing, phi by 2, and here phi naught 3 phi naught by 2, then 5 phi naught by 2, and so how it is varying. Now it clearly indicate that the screening current changing its sign when the applied flux reaches half to a flux quanta. You can see here the sign has changed when it is reaches to its half quanta. So half of a flux quantum. So then as applied flux goes from half to a flux quantum towards the 1 flux quantum, the screening current decreases. When the applied flux reaches exactly 1 flux quanta, the screening current goes to 0. You can see here at the phi naught, 2 phi naught, 3 phi naught, all the flux quanta is equal to 0. So this will depict the IS is here you can see the screening current as well as the flux. So there is a relation, this graph will show exactly whenever we move towards the half, then it is just try to get decrease. So in this manner we can get the relationship between the screening current and the flux. So at this instant the magnetic flux inside the loop, the magnetic flux inside the loop and the magnetic flux applied to the loop are equal. So there is no need for screening current. if we increase the applied magnetic flux a little more, a small screening current starts to flow in the positive direction and the cycle begins again. So, the screening current is periodic in the applied flux with a period equal to, that will be defined as the that is defined, which is the screening current of a squid is periodic in the applied flux, and the critical current of the squid depends on the screening current. So, on the basis of that, we can define the squid working. Screening current of the squid is periodic in the applied flux. The critical current of the squid depends on the screening current. So, these are the conclusion of the squid working. What is a squid magnetometer? The squid magnetometer consists of the two superconductors separated by the thin insulating layers to form the two parallel Josephson junction, and the device may be confined or configured as a magnetometer to detect the incredibly small magnetic field, small enough to measure the magnetic field in the living organism also. So, squid have been used to measure the magnetic field in any animal or in any human being. Like if we measure the magnetic field in the mouse brain to the test whether there might be enough magnetism to attribute their navigation ability to an internal compass. So, threshold value of this squid is 10 power minus 14 Tesla. Magnetic field of heart is the 10 power minus 10 Tesla. Magnetic field of brain is 10 to the power minus 13 Tesla. So, squid having ability just to calculate the squid that calculate the magnetic field of a very low quantity. So, as you can see that threshold of the squid is 10 power minus 14 and the heart threshold is 10 power minus 10 Tesla. Moreover, the brain having the 10 power minus 13 Tesla that can be measured through the squid. The great sensitivity of the squid devices is associated with measuring changes in the magnetic field, that is associated with the one flux quantum. Means we can change, we can also calculate the variation of the magnetic field. One of the discoveries associated with the Josephson junction was that the flux is quantized in the units. You can see the value of flux phi naught is equal to 2 pi h cut by 2e, all are the constant quantity. We can put this value and we can have the phi naught, that is the flux is quantized in the unit, that is 2.0678 in 10 power minus 15 Tesla meter square. So, if a constant biasing current is maintained in the squid device, the measured voltage oscillates with changes in the phase at the two junction, which basically depends upon the change in magnetic flux. So, counting the oscillations allows us to evaluate the flux change which has occurred. So, you can see on the screen, this is very much easily defined. We are having two superconductors that are attached with the insulating material, and you can see how the magnetic flux is flowing inside the device. So, this is one of the magnetic flux flow or the magnetic flux field inside a superconductor in the squid. So, squid magnetometer sensitivity can be measured, and as it is the most sensitive and the measurement devices for which is known to the man according to the Josephson Clark, one of the developers of the concept, he evokes the following images to illustrate its sensitivity. So, it can measure the magnetic field on the order of the one flux quantum. So, a flux quantum can be visualized as the magnetic flux of the Earth's magnetic field, which is 0.5 Gauss, or we can say that it is 0.5 into 10 to the power minus 4 Tesla through a single human red blood cell having a diameter about the 7 microns. So it can measure extremely tiny magnetic field. The energy associated with the smallest detectable changes in the second about the 10⁻32 joules, and is about equivalent to the work required to raise a single electron 1 millimeter in the Earth's gravitational field. So the sensitivity of the basic squid can be increased by attaching it to a flat coil of the superconducting wire. So that is called the flux transformer. So this increases the current induced in the junction and permits the detection of the magnetic field as small as 10⁻−15 Tesla or 1 femtotesla. We will continue this in the next lecture. Thank you very much.